Okay, so there we go. It has been recorded, or we're working on recording it. Okay. Without random variation, so what that random variation is, without that, that means all my points would fall exactly on the population regression line, which we know is not the case. So therefore, we're going to include some variability into my model to alleviate for that. So this is going to be written as the mean of y is equal to b sub naught, which is going to be my y-intercept. And we have b sub 1, which is my slope, times x. And remember that b sub 1, a formula for my formula sheet, is going to be r times the standard deviation of y with the standard deviation of x. So there's a lot of different things that we got to pull back into our brains as far as doing that goes. I am not for sure what exactly, I have not given you so in working through this, I have not given you this cheat sheet for assumptions. So that's something I got to get printed out and put out there. Down below, I actually inputted them down below. They're down here in my assumptions. So we'll get to those here in a second. Just as a reminder of all the different things in linear regression, we have the coefficient of determination. That is going to be my r-squared value. So remember, that is the proportion of variation in y that can be attributed to the approximate linear relationship between x and y, as I read that to you. But remember, it's how much variability is pulled out by putting it as a two variables regression versus just a one variable guess type thing. The other thing that we have in here is our correlation coefficient. Remember, our correlation coefficient is referred to by R. Okay, and remember that that's our R can show us strength and direction. DSS was a former model that we used. It was direction, shape, and strength. I forgot to update this. If that works for you, do it. When we went through linear regression, we used the SOFA model, which remember stood for strength, outliers, form, and association direction. Okay. Again, some of this is going to be a little bit of review of linear regression stuff. So back in linear regression, we talked about how to find the variance, or r squared. It's going to be 1 minus the standard, the residual divided by the standard of my total. And again, this is for computer output. And that's another formula that we're just going to remember as we go through this, okay? So how we are actually going to work with two different things when it comes to regression. We're going to work with we're going to create a confidence interval for my slope, and we're also going to we're going to do a hypothesis test on a probability of a given slope, and we'll get to that when we get to that. But in either case, we're going to be using a t-distribution again. So to do the t-distribution, because there's two different variables going on here, this is going to be n minus 2 is going to be my degrees of freedom. Okay. To do a confidence interval, my confidence interval is going to look like this. We're going to start out with B1, which is my slope. Plus or minus, we're going to have that critical t value. And again, I'm going to apologize for the shape of this first page. It is just all, I mean, look how that space I'm wasting down there. But I don't know. It is what it is. We'll have to move on. Okay. Times the standard error of the slope. All right, now when it comes down, and this is the hard part about this particular these last two skills, so to speak, because they are at the end. Sometimes they get ignored. I mean, if you ask any stats teacher, if you had get short at the end of the year, what are you going to cut out? Well, you're going to cut out these two things because they typically don't appear tons. So, but we need to be prepared should they appear. We don't have to take losses just because didn't want to have to get to it. But when we talk about the assumptions, if we're doing a interval or a test, the assumptions for linear regression are different from all my other assumptions. Okay. Now, with that said, this is one of those cases where I doubt we'll ever see anything like this on a free response question. I think it's going to pop up if you see it at all on a multiple choice question. So it's just understanding how to deal with that. And we're probably not going to have to know assumptions, but our assumptions roll a little bit differently. There's actually 5 of them. We had to show that it's linear. The scatter plot needs to show a linear relationship. The residuals plot then also does not have a curved pattern. Okay. Now I stole this from something else and forgot to proofread it very nicely. So that's not needed. Okay. Independent. Okay. Again, this is going to be sampling without replacement. If we have to show that we're not going to have any independency issues if I don't replace my variable or my data. Normal, the dot plot residuals shows strong skew or outliers. And again, I did a horrible job of proofreading this. We don't have to uphold it from something else. We don't have to make one and do it right. The residuals plot shows no clear sideways Christmas tree pattern, and it's going to be random. Okay. And actually equal standard deviation. So again, I have botched my way through this. And again, it's not a, I don't say it's not a big deal because again, we're not going to see this on a free response question. We just aren't. But there's the assumptions. Typically, I'm going to say we're just going to blow through the assumptions. But for this year, I thought we'd go through them, and I didn't do a very good job of even doing that. Okay. All right. So all this is going to be pretty much generated from a computer output. So if remember from a computer output, we'll just highlight the things that we need to make sure that we're paying back attention to again. So this goes back to Unit 2 back in September. This is a kind of a review of that a little bit. Okay, so again, if we are given a model here, the percent of fat, which is going to be Y. So this again is my response variable. Okay, and we have a model for that. So we're going to change some colors here and try to color coordinate this, which is probably more than I really needed to do here, but we'll do it. So first of all, my constant is my Y. This is my Y-intercept. This age, oops, not what I wanted to do. Undo that, back to the highlighter. This guy right here is going to be my explanatory variable. And this is going to be my slope. Okay, that is the only, and then if we go further down, this is going to be the standard deviation of the linear regression model. Again, R squared. We're not going to use the R squared adjusted. We're always going to use the R squared. Remember, scrolling back up here, R squared is your coefficient of determination. And typically they do not give you an R value. Since they gave you R squared, we can square root it to get R. Okay. If you remember from up above, we had that hand calculation of R squared. So here is going to be the residual error. If we scroll up here, Okay, whoop, a little higher. We had the residual error divided by the total error. We had those two things. If we're ever asked to calculate that by hand, here's my residual error and here's the total error. So there's those two numbers if we were trying to get that figured out. So, but we weren't. Okay, the next thing, the other two things that come into play here, as far as new things go, so this is the stuff that we have to be able to do new-wise. We're going to be grabbing this guy right here. Okay, this is going to be the standard error of the slope. And then this guy right here. This is the probability of the slope equaling 0. Okay, so again, this is all review except for those last two things in blue, where we're going to find the standard error of the slope and where we're going to find the p-value, with my null hypothesis being the slope is 0. All right, so here we go. A thrill seeker wanting to travel across a large field while being suspended in the air by holding on to balloons. In order to determine the number of balloons needed per pound of weight, he did a preliminary study. He selected a random sample of 20 rocks of various sizes. He weighed each one and also determined how many balloons were needed to lift the rock. Here's an output from a least squares regression analysis of the data. Okay, so again, this is the number of balloons versus weight. We can see that again, here is weight. So this means that this is my explanatory variable. So I'm using weight to explain the number of balloons that we're going to do. So just as a refresher, so this is not anywhere in the problem, but if I was asked to predict the number of balloons, so balloons hat is equal to, sorry, I didn't realize, I just blew a hair off my iPad. Just didn't realize I just blew right in the microphone. My apologies. 6.211. That is my y-intercept because that is my constant. Okay. Plus, because my slope is positive, 30.4126 times the weight of the rock. Okay, so that goes back to unit 2. That's a linear. We'd have to come up with a linear regression model for this situation. We're going to use the weight of the rock to predict how many balloons I would need. So therefore, when the thrill seeker would know how many balloons do I need to put on here to actually float myself across the field, is what they're after. Okay, construct and interpret a 90% confidence interval for the slope of the regression line. So we have to remember what our confidence interval is, and I got to get myself to the right set of notes that I filled out already. Okay. We know that from page 1, this is going to be this given slope plus or minus a critical t-value times the standard error of the slope. Okay, so it works exactly like any other confidence interval has. We're going to start with a point estimate in the middle. Well, that's going to be the constructed slope. Okay, the constructed slope that we did here is going to be this guy right there. Okay, or again, that guy there. So we're going to start out with 30.4126 plus or minus. Okay, this actually serves as a nice little refresher. We are trying to interpret a 90% confidence interval, which means we need some type of critical t-value. So in order to find that t-value, we're going to use an inverse t. When we inverse t, we need the area followed by the degrees of freedom. So the area that we're trying to find, I have a 90% confidence interval in the middle, which means that we have 5% on each tail. So that means if we're going the left side or the right side, either way, we're going to do a 0.05. That is the area that we're trying to find. Next is degrees of freedom, and this is going to be n minus 2. So if I had a sample of 20 rocks, n equals 20. that means that we're going to have 18 degrees of freedom. And we go to our calculator again. If we can go to our calculator. Okay. I didn't. So again, that's going to be in your distribution. So second distribution, we're going to choose inverse t, option 4. I ran this last night when I was putting my notes together, so it's already there. So we just put enter, and we're going to inverse t that, and we're going to get a negative 1.734. Okay. Now again, and because of the plus or minus, I'm not worried about the negative sign. I'm just going to write down a 1.73. So that means we're going to get a 1.73 times the standard error, which is going to be 30. No, so here, this is what we got to pay attention to. Here is going to be the standard error of my slope, not the standard deviation of the model, but the standard error of my slope, the 2.0416. And this is going to end up being a hand calculation. We're gonna, there's just, our calculator does not do this. If you, so since I just spoke it, let's go back out to it. Okay, if we go into our calculator and go stats and go over to test and scroll up, we see there's actually a linear regression t-test and a linear regression t-interval. Okay, let's do that. So I select the tentative interval, and we can see that's asking me for an X list and a Y list. So your calculator will do that if you have data. If we're doing this from a computer output, this is going to be completely hand calculation. So I have already done that for us. So that is going to be 26.87 on the low end to 33.94 on the high end. So we have created an interval. And now again, we're going to go back to, we are, as said, construct and interpret. So that means we are 90% confident the true slope of the least squares regression line between weight and balloons, so we got to get that context back in there, is between 26.87 and 33.94. Oh my, we gotta have some units on here. What is the unit of my slope? Okay, so again, we have, again, my slope is going to be change in y over the change in x. All right, that's a slope, right? All right, so the change in y is going to be balloons. And then we're going to divide by my change in y, which is going to be pounds. So it's balloons per pound. Strange unit. Okay. Moving forward. Yes, that works. Okay, sorry. The other thing that we can do with this, and again, it's not nearly as formal as our other one, is that we can do a hypothesis test for a slope as well. And it says make a conclusion based upon 0.05. So again, because this is a hypothesis test, in reality, our phantoms will work here. But also in reality, again, the expectation that this is a free response question, the p-value of that would be very, very small. Okay, so I'm not expecting this, but we at least need to know what happens in the process. So it says write the hypothesis for this. So here's what happens. In a hypothesis test about slope, okay, inference about slope, our null hypothesis is my slope is equal to 0. So again, this is the same thing as we're going to assume there's no relationship between two variables. We're going to assume there's no independence. Okay, we're going to assume that there is when we're doing a goodness of fit test or a homogeneity test. Okay, we're going to assume that the distribution is the same. Okay, so we're assuming that just like this, we're going to assume that there is no relationship between two variables, because if there is no relationship between two variables, I'll go back here to some random spot, we would expect a scatter plot that would have a distribution that looks something like that. And if we were to ask a line of best fit, my line of best fit would go through there like that, and it's a horizontal line. So therefore, the slope of this horizontal line is going to be 0. So that is what my assumption is. I am going to assume the slope is 0. Okay, so that's my null hypothesis. My alternate hypothesis is pretty simple. My slope is not equal to 0. Now I've introduced a variable here. Okay, so B is the true slope of the least squares regression line between. So this is like the end of my statement for my interval between weight and balloons. So again, if we were doing phantoms, again, this is where we'd list out anything that we'd want to list out. We'd wrote out hypothesis statements. Our assumptions were not going to roll through. I just wanted you to see them. The name of this. So this is going to be a t-test for linear regression, if we had to name it. It did not tell me to do that, but we might as well just throw it in there. Okay. My test statistic, again, it's actually up here as well. It's the 14, but that's the p-value that we're after. Actually, it just wanted me to write the test, write the hypotheses, and make a decision. So up there's the two things that we need. We're going to have a p-value of approximately 0. Okay, so we're going to make a decision. Since the p-value is less than alpha, we will reject HO. So HO again, okay, and I'm butchering this up horribly. HO again is my null hypothesis that the slope is equal to 0. So this p-value, again, remember what a p-value is, given my null hypothesis is true. So given that the slope, there is no linear relationship between my two variables. So given the slope is 0, okay, the likely there actually it's given that there's no relationship between the two variables, the likelihood of having a slope of 0 is 0. So this is just not going to happen. Okay, that means there has to be a relationship between the two. Okay, so there is sufficient evidence to say that the slope is not equal to 0. Okay, and we move from there. That's just to tell us that there is going to be a linear relationship here. Again, this isn't used a ton in AP statistics, okay? But it is on the list of things that we have to cover, so here we are. All right, let's go to the next problem. Example 2. Mars rocks contain a high proportion of silicon dioxide and much smaller amounts of titanium dioxide. The computer printout shows the regression of titanium dioxide percentage versus silicon dioxide percentage for 5 Mars rocks. Okay. So again, if we go back and we're trying to pick out things that we need to pick out, here's my constant. Here's 2.7962. That is going to be my y-intercept. It looks like the percent of silicon dioxide is going to be my explanatory variable, and it has a slope of that. Okay, so when we go to write that later on, okay, that's the pieces parts that we're going to get. Okay. Now it says, question A, what does the value S equals 0.0257 tell us? Be specific. So here is S is 0.0257. Okay, so we have to remember that that is my standard deviation. So a standard deviation, so this is all going back to unit. I mean, this is a nice review of unit 2, okay? Back to September. The typical point. Now it looks like paint. Sorry. gotten off track here. The typical point deviates 0.0257% TiO2 from the regression line, because that'll be the variable of my response variable, or the unit of my response variable. Basically, again, that is my residual. Okay, it's been a while since we did some of this stuff, so that's why this problem is here. It says interpret the coefficient of determination, or R squared, so we can come back up here. We can find R squared. R squared is 96.1%. So that means that 96.1% of the variability, horrible. Try again. (96.1%) of the variability in my response variable, which is TiO2, can be explained by the least squares regression line between titanium dioxide and silicon dioxide. Okay, again, this is so until we get to, it looks like D. Okay, we got one more. D, we'll get to new material. Find and interpret R, the correlation coefficient. All right, so again, R is going to equal the square root of whatever my R squared value is, which is going to be 0.961. So we're going to find out what the square root of that is. I know what it is. It's 0.90803. Now here's the thing that this is why this example is in here. If I go back up to my slope is negative. So what I had to remember that because R shows me strength and direction, I had to remember that negative sign is also going to play into my R value. So that R value is negative 0.983. Okay. So the relationship between TiO2 and SiO2 is negative and strong. Okay. Find and interpret a 90% confidence interval for the slope. Okay. So again, we're going to start, again, I'll go ahead and write this out. It's B plus or minus my critical T value times the standard error of my slope. So now it's finding all those things. Okay. So my slope. Sorry, I'm like, oh, never mind. I was looking at my notes and I got confused. Yes. 0.0337. I'll just cut it off there. If you wrote out all to the 2.8, I didn't save myself much by not doing that. I don't know why I stopped. Okay. We need a critical T value. So let's come over here and figure out what T is. We're going to inverse T. Again, we're still talking about a 5% tail and degrees of freedom. Let's see here. Did it give us a size N? Well, okay. It told us we had 3 degrees of freedom. Yes, because we had 5 Mars rocks. If we ran out to my calculator and did that, this would turn into a 2.35. So that means that we're going to have 2.35 times 0.00, whoop, make sure we're grabbing the right number, this guy right there, my standard error of my slope, 0.0039. And when we do that, we get an interval that is a negative 0.043 to a negative 0.0245. So that means that we are 90% confident the true slope of the least squares regression line between TiO2 and SiO2 lies between negative 0.043 and negative 0.0245 percent. It's an odd unit percent per percent. So I guess that cancels out. You wouldn't need a unit on that one. It's kind of crazy. Okay. If we, again, this is going to go back to a little bit of intervals. If we increase my confidence level to 99%, what is going to happen to the interval? And I'm just looking for a generality here. Okay. It would become, and this is two choices, narrower or wider. This is where I should have you type it in to make sure you're all paying attention, but it doesn't, who knows? There we go. It would become wider. Again, I want to be more confident. The more confident I want to be, the wider I have to cast my net. So therefore, it would become wider. Okay. Again, going back to sample sizes, if we increased the sample size, that means my degrees of freedom is going to increase here, and my interval would become narrower. Is the test that was conducted statistically significant? Well, I didn't really say that there was a test done. However, if we scroll back up here, here's the percent, here's my slope. Okay, here's my slope, excuse me, my explanatory variable, my slope, the standard error of my slope, and if I come over here, here is going to be my probability. So the probability of my slope being 0 is 0.0083. So is it statistically significant? Yes. Since my p-value equals 0.0033. The likelihood, spelled wrong, of a non-linear relationship is very small. Indicating relationship is linear. Okay. So this one works a little bit different here as far as instead of having a homework packet and a notes packet, I just put your homework or your notes. I put your homework first and I put your notes first and your homework second. So if we go through the packet now, we have looks like 1, 2, 3, 3 different problems to do for that. Okay. I know last night I sent out that we were going to we weren't going to do the 9B. We were going to wait till Thursday, Friday to do 9B. But then when I was filling out the keys last night, I'm like, no, let's just get it wrapped out today. So I apologize, but I have changed my mind. And if now that I think about that, I put you guys at a disadvantage if you haven't printed off 9B yet, because you weren't expecting that it would come. So I will try to stall here for a second. If that's, if you need to adjust something, get a piece of scratch paper to write down answers. Again, I'll post the key. You can go and do that later if you need. But I would like to get a shot at rolling with 9B, and we'll see where that goes. Okay, because I think we can quickly pound out the notes for this as well. And as I say that, I realize there's a lot of data entry here that's probably going to take more than the 20 minutes left of my allotted time. I'm stuck here because I just want to feel like I wasted time today, or I'm kind of wasting away on this week. Let's do this. Let's come back. We'll come back Wednesday, and we will actually do notes on Wednesday, which is actually something that I usually don't do, but I'll cut it off for the day. We'll do 9B notes on Wednesday, and we'll go from there. Because I said the activity was a maybe, and we just won't worry about the activity. I feel like I'm going to fritter away time, and it's going to be AP testing weeks before we know it, and then you guys, it's really hard to review during AP testing weeks. So I'm going to stop the recording.